there's been a lot of progress in the optimization community for developing fast and efficient algorithms for solving convex optimization problems. Most of these algorithms rely on the sophisticated interior point methods, which were developed in the 80s and 90s and was considered a revolution in optimization. They're very efficient algorithms, have theoretical polynomial time runtime guarantees. And by polynomial time, I mean these algorithms' runtime is polynomial in the dimension of the problem as opposed to exponential. So they scale with the dimension of the problem. Developments or advances in the storage, sensing, acquisition technologies, as well as the development of online platforms, automated markets, enabled us to collect and acquire much more large-scale and finer data, whether it's tick-by-tick price data from the stock market or frame-by-frame high-resolution images from surveillance systems. So the data sets that we're dealing now are very large-scale. They contain hundreds of millions, billions of data points, and they're very large dimensional because they're very rich. They can capture very rich features and characteristics. And because of the scale, their storage and even collection is most of the time done in a decentralized manner. So this made basically this trend, this very large-scale data trend is referred to as the big data, very popular term in industry. And this made essentially the sophisticated popular interior point methods impractical, because while being polynomial time methods, these methods have runtimes which are dimension dependent, meaning if the dimension is very, very large, just a single iteration of these algorithms will take a long time. So this created a big change in the optimization community, and over the past 10 years shifted the focus to much simpler so-called first order or gradient methods, which are very simple methods that involve simple computations. The interesting feature of these methods is that their runtimes have very mild dimension dependence. We can say essentially dimension independent. And also, because they're very simple, they lead to distributed implementations. So my work in this area focuses on such methods over the past 10 years and develops fast and efficient algorithms that can process very large-scale data that are distributed and also potentially dynamically available. So certainly, I think these methods have the potential to be able to process very large-scale data. So I'm really looking very much for partnerships in which we can have access to these large-scale, rich data sets and use these algorithms to process, make predictions as well as decisions based on these algorithms. It's basically, it could involve all kinds of relations ranging from access to data, algorithms which are motivated by the nature of the problem, so tuning and designing new algorithms that can actually process these different kinds of data, to potential collaborations in terms of student internships and visiting researchers that we can actually cultivate these collaborations.